Now today, I didn't give you homework. I want to make sure. But today, I will give you homework, and it's going to be on power. I want to make sure everybody's on, just stays with me. What I really wanted to do last time, I wanted to make sure that you saw how to apply all the concepts, Thevenin, Norton, really superposition. Well, we didn't do superposition, but mesh nodal circuits with complex impedances. Follow me? So now we've done everything with complex impedances. We've done it with just strictly real resistances. Now we're going to move on, and you've had transits too. Now we're going to move on to power. And I want to be clear about this. Power, in terms of engineering and physics, is really something where it's the rate at which being done. When you think of a 50 horsepower motor or a 1,000-watt generator or anything like that, that gives you an idea of power and what they can or can't do with the power. Now, so with ours, when we talk about electrical circuits and power, we're talking primarily about that wall outlet there, which is at 60 hertz, 117 volts, or we're talking about the distribution system that brought that about here. For instance, if you take a look at this right there, that's plus or minus 117 volts RMS that I'll explain today at 60 hertz. It's called one phase. Technically, there are three phases that are actually transferred that I have to get to. But on the other side of this, there's something called a transformer. If I trace that line up to the pole, and on the other side of this would be a 7,200 volt system. Now that's the system, if you get across, it's probably going to kill you. This won't, usually. Then that 7,200 volt system gets bumped up to somewhere between 50,000 and 100,000 volts. And then when it's transferred long range, you're talking about very, very high voltages, upwards of 750,000 volts on these very high guy wires you see there. But they are not pulling a lot of current, and that's where we get to power. We're going to be talking about power. So that's what we're primarily talking about. Something at a constant frequency generally. All right, 60 hertz for this country. Do you know what it is in Europe, anybody? Anybody? 50 hertz. In Europe, it's 50 hertz. Their volts higher, about 225 peak volts? That's 117. But we'll talk about that. So, now, some of this is from last time. I'm going to just recap it. When I talk about power P of T, that's V of T times I of T. And when we think of power, it's instantaneous power. We have any device at all. You can say it doesn't matter what this device is, but it's going to develop a voltage V of T across it, and there'll be a current I of T into it. And this is the power right there. The units of power that we use are watts. The abbreviation is just W. Voltage is volts, current is amps. Amps times volts is watts. Got it? Now, after that, last time I said, well, for our systems that we're interested in, we're going to have a current I of T. Most systems, not all, but most systems. Matter of fact, you're going to see after the first two sections that we cover here, everything will be at a constant frequency, sinusoidal variation. We're going to have some Im cosine of omega t plus some theta I. And we're going to have some V of t that's equal to Vm. And the sub m means magnitude. That's the magnitude of the current. It could be like 10, 100, whatever. And it's times cosine of omega t plus theta V. Now, when we take a look at this, the instantaneous power, P of t, since it's equal to V times I, I'm going to use the cosine identity that I did last time. Remember, I did this. I said cosine of A, really cosine of A times cosine of B is equal to 1/2 times quantity cosine of A plus B plus cosine of A minus B. You don't have to memorize that one, just realize that that's the only thing I'm doing here. When I plug that in here, I get 1/2 times the quantity of VMIM. Then it's times cosine of 2 omega t plus theta V plus theta I. This is just something for the record books. We're going to forget about this in a second. Plus cosine of theta V minus theta I. I want you to realize that's what it comes down to. That's instantaneous power. and that's omega t. Try to make it a little better. That's 2 omega t. Y'all remember that? Now, after that, we took the average power, and we said P av, the average power, was equal to 1 over t, where t is going to be the period, the integration from 0 to t of P of t dt. Instead of rewriting that whole thing, I'm just going to talk my way through it. This term right here is a constant. Theta v minus theta I, the angular difference between voltage and current is a constant. Follow me? If the load doesn't change. If you have a given load, that will always be the same. Since it is a constant, when we take and average that, that's just going to come out to its own value. So it will be just 1/2 Vm Im times. Remember this from last time class. Now, this is variable. Omega is the radian frequency. And in case you don't know, omega is equal to 2 pi times s, where f would be in hertz or cycles per second. Are you with me? So omega is 2 pi. How many are familiar with the term omega? I mean, from physics and all your other things, you should be very familiar with, very comfortable with it. Period is the length of time over which a full cycle develops, right? And the period is 2 pi radians, right? In terms of an angular thing, or it can be, the period can be in a time, the length of time that it takes. And t is usually given in time in this stuff. So the period is 1 over the frequency, by the way. So t is equal to 1 over the frequency, or t is equal to 2 pi over omega. And either one. Now, when you do this calculation, the thing to take from it is, this is a cosine waveform that's varying, right? Remember, the integral of a cosine waveform over one period is, class, how many know it's 0? A cosine or sine integrated from 0 to 360 degrees, or 0 to 2 pi radians, is 0. Do y'all follow me in this? If you integrate it over 2 cycles, it's still the same, 2 periods. So that means this time variation will be taken out of it. And the average power here simply becomes, and write that down, 1/2 Vm times Im times the cosine of theta v minus theta I. We're going to come back to this term in a bit. That's actually called the power factor. Now, what does that mean for us in terms of the standard stuff that we deal with? So, or the standard problems we run into. So I'm going to try to do that right here. We did this last time. All right, first, if we have a resistor, here, all right, if I have a voltage across that resistor V of t, all right, and let's let V of t be equal to just some Vm cosine of omega t. Are you with me? That's going to give rise to a time varying current. If that's V of t, I of t here will be that value, V of m, times cosine of omega t, divided by the resistance. Does everybody follow me? This isn't the time delay. You give me a value of voltage, I'll give you the value of current. Now, the average power through there, the instantaneous power would be V of t times I of t. That would be equal to just V of m, right? Right, times cosine omega t times V of m over r cosine omega t, or V of m squared over r cosine of omega t squared. Do y'all follow me in this class? How many do right here? I'm just taking the voltage and the current that I found by assuming a voltage, right? Can you all see this in far back? You guys can see it? All right, now, when I look at the average value of this power, right? Well, the average value of that power would be 1/2, well, I'm sorry. It would actually be equal to 1 over t, the integral from 0 to t of that. Now watch this, Vm squared over r is a constant. But y'all remember cosine omega t from the back in the day, the half angle stuff you had, or all the trig identities? That was equal to what? That's simply 1/2, right, times 1 plus cosine of 2 omega t dt. Y'all remember that? As a matter of fact, you can get that by just going back to this thing, and theta v minus theta I was 0, right? Follow me on this here? Because there's no difference, phase difference in voltage and current for a resistor. You all see this class. So you end up getting this. Now, what do you notice happens here? What happens to 1 dt times 1/2 Vm squared integrated from 0 to t, 1 over t in front of it? You all see that's just going to bring out a constant. If you integrate a constant from 0 to t, you get t, right? Then if you divide by t, you just get the constant. You all see that, class? Here, you're only going to get 1/2 Vm, that's magnitude squared, over the resistance. Now, what about this part, the cosine of 2 omega t dt? Well, that's varying, right? It has positive and negative values, right? But if you integrate that over any period or any n period, you get 0. You all follow me on this? So this term has no effect. That's what it is, and that's the average power that's dissipated. They call it the effective power sometimes, but average power dissipated in a resistor. A resistor is the only element of the three that you're familiar with, capacitors and inductors or resistors, that can dissipate power. By dissipation, it takes it, when I say dissipate power, it means like if you put power, electrical power, into a heating element and it heats the water, all right, then it's dissipating the power into the waters, the environment, all right? It's dissipating the power. It's changing, you might say, the form that it's in. So if you take electrical power and heat something, then it becomes thermal energy. Got me on this one? This is the only thing that dissipates power. The inductor and the capacitor don't. So that's a resistor. Next element we talk about is going to be a capacitor. Let me erase all of this. I want to get to the important stuff, but I have to go through the basics right here. So if we have a capacitor here, all right, and I put a voltage across it, let's assume this voltage V of t is going to be Vm cosine of omega t, and that capacitance is C. It gives rise to a current I of t through the capacitor. Now mathematically what I is, I'm not in the phase domain, I'm in the time domain, right? What that current is going to be is C times dV dt, mathematically. Got me on this one? Are you talking about this? What were you talking about? C times dV dt. It's the time rate of change of the voltage across the capacitor. Right? C is the capacitance. Does everybody follow in this? Now, what's that going to be? Well, that's C times the derivative of this with respect to time, which means the derivative of cosine would be minus omega, right, times V of m, and that would be a sine, right, of omega t. Y'all follow me? If you just take a derivative of cosine omega t, what happens? You get minus omega sine omega t, correct? Now when you multiply these two together, you're going to see that the power P of t right here becomes V of m. It's actually going to be minus omega times C times V of m squared, and then it's going to be cosine of omega t times sine of omega t. Now that's instantaneous power, not average power. Y'all follow me? Yes?
Why do we multiply -1 to the I?
What's the derivative of cosine omega t? Just tell me. It's not I. I didn't. This is supposed to be t.
Oh, I thought
I'm
it was
sorry.
-1.
This is an argument of time. That's what I'm trying to put there. My bad. All right. Now, when you do this right here, well, I know everybody, I think most of you know that sine and cosine are related by 90 degrees, right? So sine is really cosine of omega t minus 90 degrees. I'll just put it in right here. All right. Now remember, when I started out, I said that if you had a voltage V of m cosine omega t and a current I of m cosine, well, I said V of m cosine of omega t plus theta v times the current I of m cosine of omega t plus theta I, right? If you had that, the thing you cared about was the difference in the angles that weren't related to the omega t term. You're with me? Yeah?
Could you read like, the power equation just a little bigger?
Yeah, I'll be happy to. Here's what I'm doing. I'm taking this times this. That's it. Voltage times current. All right? So if I take this V of t times I of t, I'm going to get minus C omega Vm squared, and then it's going to be times cosine of omega t times sine of omega t. That's where I was. You're going to see most of this isn't going to be important in a little bit, but for now you have to see how come it's not important. Everybody see that? Now, the sine of omega t I just changed to a cosine, and that's cosine of omega t minus 90 degrees. Now, why did I do that? Because remember when I had one equation where I had V of m cosine of omega t plus theta v, another equation, I of m cosine of omega t plus theta I, right? When you looked at the average power, what did you find? It only came down to the omega t didn't show up here. It was just going to be the magnitude of Im, magnitude of Vm, divided by 2, times the cosine of theta v minus theta I, right? Are y'all, does everybody follow me on this one? I can do this for you. I could do the averaging, but I think you can see this. If you have two waveforms that are 90 degrees out of phase with each other, and you integrate those things over a period, you get 0. How many know that? You integrate a cosine theta times the sine of theta from 0 to 2 pi radians, you get 0. It's going to happen. I can prove that, but the real thing is this. It's the angular difference between the argument here and here that you have to get, and then the cosine of that. The cosine of that, cosine of 90 is what, class? 0, right, and this is 0. My point is this. The average power dissipated by a capacitor is 0. Everybody follow me on that? That's the point. You can mathematically prove it. If this was an inductor, I'll do the inductor next. This always works. I'll leave that up there. If I have an inductor, as such, L, and now I'm going to assume a current. I'll say that I of t here is equal to some magnitude I of m times cosine of omega t. All right, so I'm assuming the current. That develops a voltage here, right? Voltage across the inductor. The voltage across an inductor is L times di of t dt. Isn't it, class? I don't know if you remember that, but both the capacitors, the voltage across the capacitor in terms of its differential equation, C dV dt is equal to I of t, as well as the voltage across an inductor in terms of the differential form, which is L, I said that wrong, IC of t is C dV dt. I'm not sure if I said that right or not. Here, it's L di dt, it's the rate of change of the current times L that gives you the voltage across that vector. I don't want to complicate this too much, but I do want to say one thing. Actually, this is an assumption that the inductance is not time varying. The actual value of that voltage across there is equal to the derivative with respect to t of the quantity L that could be a function of time times I of t. Now, the reason I put that down there, if L is a function of time, you have to take a derivative of dL dt times I of t. In this class, we don't worry about that. How many here are MEs? Mechanical engineers. You do. Not my class, but in the real world. Let me tell you why. Mechanical engineers and aerospace engineers work a lot on systems that blow up. They just do. When I was at Eglin Air Force Base, I learned a lot about things that blew up, doing consulting for them on weapons. And one thing they do to generate an enormous voltage is this. They take an inductor, without getting into specifics, because it's probably ultra classified. They take an inductor and they drive a large current through that inductor. A DC current, and I mean large, like hundreds of kiloamps, kind of a large, massive current. But then they blow it up with some high explosives. And as it's blowing up, it causes a voltage across the ends that is ginormous. It is immense, this voltage, such that you can create what's called an electromagnetic pulse flare when you drive a certain type of antenna with it. Now, you probably have watched sci-fi movies and stuff where they talk about electromagnetic pulse, right? Basically, it's a pulse that the electric field is so very large and it's got such high frequency that it penetrates anything and it blows out the front end of anything made with standard electronics. For instance, anything with any kind of chips in it that have BJTs, really transistors, it'll destroy it. But they don't always want to blow a nuclear weapon up to create that kind of effect. So they use this to do it without having bombs, mushroom clouds and stuff like this. And it is very effective for doing that. I didn't know how they did that. And here's what they basically do is they have a time varying inductor there, all right? And that causes a ginormous voltage loop. And I say that because the value is, when you hear about 1,000,000 volts, to me that's a lot, right? But you know what the breakdown strength of the air is, right? How big of a voltage difference you have to have across a meter to get electric breakdown like lightning? Anybody? At sea level. About 3 million volts per meter, right? All right, that would cause, that's what it is. We're talking about something that's getting a voltage, an effective electric field that is like 100 times that. So they're getting like 100 million volts across a couple of terminals. And when that thing arcs and stuff like this, they actually have it driving a certain type of antenna. It radiates an immense amount of electromagnetic energy over a very short time duration. I can tell you, MEs and aerospace engineers, if you get involved with this, it's fascinating. It's shocking in a sense what can be done, but it's probably also something, if you're a guy, you're gonna love it. They just do. I don't know why, but they love things that go bang.
I wouldn't. We like to go back.
How many here in the military? Oh, come on, I know you guys are. Anybody else? One, we're here? All right, well, you're gonna find out about a lot of this eventually. Pilots especially, you're gonna learn all about the fun stuff you have to do with electromagnetic pulse. All right, so for this thing with the inductor, that's the current, that's gonna be the current, therefore the voltage V of t is equal to L times VI to t, right? And that means it's gonna be L times omega, right, with a minus sign, times Im, times cosine, times sine of omega t. That's the voltage. Therefore, the power here, P of t, is equal to V of t times I of t. And it's going to be minus L omega Im squared cosine of omega t times sine of omega t. Now that's the instantaneous power. It has a peak value of instantaneous power right here. That's its magnitude, L omega Im squared. You don't need to worry about that. But the average value is 0. So the average power dissipated right here will be equal to 1 over t, the integral from 0 to t of minus L omega Im squared times cosine of omega t sine of omega t dt. And that will be 0. And the reason is I can change the sine into a cosine of omega t minus 90 degrees. You just need to know this. You need to know that the average power dissipated by that inductor is 0, the average power dissipated by the capacitor is 0, and the average power dissipated by the resistor is Vm squared over 2R. As a matter of fact, I want to do one thing with the resistor to make sure we're clear on that. When we have a resistor here, and we're driving a voltage across it, V of t is equal to Vm cosine of omega t. So it's a time-varying voltage that's periodic. It's got a frequency omega t, or a frequency omega here. It's got a value R. I can say it's got a current I of t here equal to V of m over R times cosine of omega t. When I take a look at this, the average power here will be equal to simply 1/2 times Vm squared divided by the resistance. So it's only a function of the magnitude of V of m and the value of resistance. And that's in watts. All right? Now, to do a problem. Here? Yeah, this is just taking this, it's just taking the power right here and integrating from 0 to t. It's the average value, so the average value of anything at all, will always be the value of that something versus time, integrate that value from 0 to t over a period, and then you divide by 1 over t to get the average value. That's normally done, and it's a common engineering concept when you think about average of anything. And if it was digital, if there were singular events, there would be sum of the events divided by the number of events, and that would be it, whatever the outcome of the event is. All right, now we do a simple problem to make sure everybody understands how to do this. But we're going to do this in a phasor domain. And that's going to bother you, but I'm going to show you one thing. You realize how the only thing we care about is really what? It's the magnitude of the voltage or current. We don't care about the cosine omega t, right? We care about the magnitude if we're talking about either L, C, or R. So we can actually do this in the phasor domain. And so suppose I have this. If I'm in the phasor domain, I know that if I have 12 at an angle of 0 degrees volts, that voltage is really 12 times cosine of omega t volts, right? If that's the voltage, follow me? We just don't write the omega t. We just put 12 at a certain angle. You with me? This is a phasor. Now, if I have that, and then I have a resistance of 4 ohms here, and I have a resistance of 2 ohms, and a capacitor here, let me see what I have down there, minus J1 ohm. Now remember here, the value of the capacitance you don't care about. The only thing you care about is that impedance, follow? Our goal is to get the current, and the reason we want current is because once we have current, if we have a resistor like such, and we know the current I or the voltage V, and those are magnitudes, then I can say that the average power, P_av, would be equal to either 1/2 times magnitude of Vm squared, or voltage, just voltage squared, over R, or it's equal to 1/2 times magnitude of I squared times R. And the reason you like these equations is because they're very convenient and quick to use for average power. Now it's using the magnitude of the voltage or magnitude of the current. For this one, let's take a look at this. What's the current here? Magnitude. Anyway, can you all see it? Current is what? Voltage divided by resistance, right? In the simplest sense. Well, the voltage is 12, the resistance is 4, it's 3, isn't it? So I here, I the 4 is 3 amps. Now what is I here? For that one. We can call this I1, right here, I1. What's I2? Well, same voltage, right? Please watch this. Do you agree with me? 12. Well, what am I dividing by? 2 minus J1. I put down a magnitude, 2 minus J1. That will give me the magnitude of the current. You only care about magnitude. Got me on this one? What's that magnitude going to be, anybody? I think it's 5.36. Good, amps. Don't need the angle. Don't need the angle. We can put the angle in if we want to be complete. But right now, the only thing we care about is magnitude of the current. All right? Now, how much power is being supplied by this source? This is the voltage source that's supplying the power. Well, it's going to be the power dissipated here plus the power dissipated in that resistor. This dissipates 0 power. Got it? Yes, miss.
Could I just combine them, like have them in parallel since I can combine the two into series?
I want to know what you want to put in parallel.
Okay, for the impedance, like.
We don't need the impedance. We got the current, don't we?
Oh, okay, yeah.
We got the current. That's all we're after is the current through these elements. Got it, class? The current tells the tale. Because only the resistance has average power that's dissipated. The inductor and the capacitor don't. We're only after average power, not instantaneous. So what happens here? if I want the power, the total power supplied by that 12 ohms, or by the 12 volt source, this would be P supplied, would be the power there, which would be what? 1/2, the magnitude there is 3, right, squared, divided by 4. Are you with me what I'm doing here? I'm taking, times 4. That's going to be I squared R divided by 2. It's this form I'm using. So 3 squared is I squared divided by 2. That would be the power of the 4 ohm plus the power deposited in the 2 ohm. Now you need the magnitude of current to that. So it's going to be 1/2 times 2, right, times the I squared, which is 5.36 squared. What do you get for that? Well, let's see. That's going to be 9 times 2, or 18 for the first one, right? And for the second one, what do you get? 28.8? I've done this one. Is it 28.8 for the second one?
Yeah, 1
All right. So the total power dissipated by both of those resistances would be the sum, and that would be the power supply. That's the only thing I'm trying to show you how to calculate power for a circuit like this. You get the current. The power, average power dissipated by an inductor or capacitor is 0. Everybody understand that? Now really, what's going on with an inductor or capacitors? They're energy storage devices. What you basically get is a magnetic field that's created around an inductor that has energy in it, and then the energy is dumped back into the circuit. It's swashing back and forth. Same with a capacitor. Capacitor stores electrostatic energy, then it dumps it back in the circuit. A resistor burns it up. So a resistor literally is something that dissipates heat. That's the thing we really kind of think about. You could say, well, it's light too. Yeah, photons of light usually interact with the atmosphere and the environment and create heat eventually anyway, all right? And there's a lot of other things that we could talk about. It can be mechanical motion. It can be anything, but resistance is something that always dissipates power. All right, now, next concept, because there's stuff I'm going to show you, and I'll tell you what's really important. This is sort of, the key to take from this is when you want average power that we always want, you want to find out the current, and once you got the current, you just take that current, square it if it's magnitude, multiply by the resistance by 2, that's the power in each ohm, got it? But you have to get the current. That was the bottom line of this. And the average power dissipated by by capacitors and inductors is 0. So next, we go to something that helps us get an understanding on what's called the effective value of the current and voltage. And I want to do this one with care. I'm trying to get somewhere, but I don't want to do it in too much of a hurry. So, some of you probably, how many have heard of the term root mean squared, or RMS surface area, RMS anything, right? In your own words, what does RMS mean to you? If you're a mechanical engineer and you talk about the RMS surface area on a plane, in your own words, what does it give you? It's a measure of the effective error that you can expect, right? If you have an RMS error, RMS anything, it always means what's effectively like that if it was, if I wanted to just, think of this, if you want a constant value of error everywhere, that would be the constant value of error, if that makes sense to you. So when we talk about RMS, it stands for root, square root to be honest with you, and then mean. So a mean is an average square. So it's going to be the square root of the mean of the square of the thing. So when I talk about RMS value for current, it's actually the square root. I think you MAs and probably the aerospace engineers, maybe the industrials, I'm not sure. You're familiar with this, but it's common. This would be equal to the integral from 1 over t from 0 to t. So it's an average of I squared of t dt. So it's an average of the squared value and then the square root of that. That's called RMS. Do you remember this from your other courses class? Give me a show of hands if you do. I know the MEs know this stuff, all right? And I'm sure Aero has to. Industrial, I'm not certain, but it's an effective value, that quantity. So that's IRMS. Now, I'm going to do, most of the time, we only worry about sinusoidal waveforms and the relationship between peak value and RMS value. But just for completeness, we have to take a look at it for waveforms that occur commonly in electrical circuits, but they're usually not affiliated with an RMS values. But he does it in his book, and it is worth doing. Suppose I had this. This is my I of t. This is going to be time, and the waveform does this. Oops. All right, and this is a good example for a lot of things. This is going to be 1 second, 2 seconds, 3 seconds, 4 seconds, da da da. The time axis is going to be in seconds. So here's what we want, and I got to give you the magnitude of this. This has a magnitude down here of -4 and constant. This goes up to 4 here, and the units are going to be amps. So this is a current waveform. Assume it's periodic, all right? So it would just keep on repeating itself. And the period is 4, understand? It's the length of time it takes before for it to repeat itself. So now, I'm going to do this. Let me take this. Period is 4, right? Now, what I want to do is execute this right here. I'm just going to put the numbers into it. Before I can do that, I need an equation for this straight line, don't I? Well, I know that the equation for a straight line is mx plus b, or in this case, mt plus b, right? And b is the zero intercept. Here you can see that it intersects 0 at t equals 0, so that b is 0. I just need the slope of that line. Do y'all agree with that? Since I go up to 4 at 2 seconds, the slope is 2, correct? Everybody see this? Therefore, the equation for the line here from 0 to 2 is simply I of t is equal to 2t, period. Agree? Now the equation for the line between 2 and 4 is just I of t is equal to -4. That's it. Nothing tricky here. Got me? Now, I'm going to just execute, or do that. I'm going to do what it says. When I look at IRMS, I know I have to take the square root, right? 1 over t, or 1 over 4, of the integral of I of t squared dt. Well, my first I of t is going to be from 0 to 2 of 2t squared dt, plus the integral from 2 to 4 of -4 squared dt. Y'all see what I'm doing? I'm just literally sticking the numerical values in for the equation I had otherwise. Well, this is a straightforward thing. So IRMS here, my IRMS for this waveform, will be equal to the square root. And now look, I have 1/4 there. When I take this, the 2 squared is 4, right? Coming out the front, then I have t squared dt is t cubed over 3, right? From 0 to 2, so I have 2 cubed over 3 here, plus, and then it's going to be -4 squared, which is just 16 times 2. Y'all agree with me? Now, it doesn't matter how you go about it from this point on. You can use the calculator if you want. You can see one thing for sure. When I take that 4 and divide through it, I get rid of the 4 here, right? And I have 2 squared over 3, right? Or 2 cubed over 3, which is 8/3 there. Do you agree? And then for the second part, I have 4 into 16 is 4 times 2 is 8, correct? So what do you get? Your IRMS is what? Square root of, in that case, it's going to be 8/3. And in the second case, it's going to be +8. And what's that value? Just punch it into your calculator. I think I got this. 3.27x, is that right? Anybody? I think it's right. Class? Is that right?
Yeah, 3.27.
Thank you. But this is a straightforward operation. Most of you have seen things like this before. You're looking at some sort of an effective measure. This, in our case, it's the root mean squared, or the I effective. And we could do more problems, but this says it all. Now, it's the same thing for voltage. If they want VRMS, it would be V squared here, dt, from integrated from 1 over t times 1 over t in front. Understand? So really, if it's I, it's I. If it's v, it's v. That's it. Okay? Now, here's the thing that's important, what I'm about to show you. It's the relationship between the RMS value of voltage. If you have, yes,
Why is it not minus 16 times 2 since
it's minus squared, right? It's I squared, minus times minus is plus. All right, next, what we're going to be talking about is the relationship between RMS values and peak values for sinusoidal waveforms. This is important for things like that right there. The wall outlet is a sinusoidal or cosinusoidal variation. So if we have V of t equal to Vm cosine of omega t, right? And I can go ahead and put plus theta. I'm used to seeing this translate into a phasor, Vm, at an angle theta right here. And this is going to be volts, right? But it's the peak voltage, right? It's the voltage coefficient in front of the cosine. Now, how does that relate to the RMS value of this voltage? Well, if I wanted the RMS value, Vrms would be equal to the square root of 1 over t, the integral from 0 to t. And by the way, you know, t is equal to omega over, sorry, 2 pi over omega. If you want to, you can actually play this stuff in there, put it in there and do the integration, but I'm going to show you what happens there. Now it's going to be equal to the square of that. V got a squared, so now I have Vm squared, and it'll be cosine squared of omega t plus theta. And then it's going to be dt. Okay? Now, remember what I did before with a cosine squared of theta. I'll put it here. You don't have to know this, but it's nice. The cosine squared of theta is equal to 1/2, all right, plus 1/2 cosine of 2 theta. Anybody remember that at all? You've seen that a lot. If you're ME or Aero, probably you see it all the time because you have to use that kind of stuff routinely, those identities. Well, here, the 1/2 is a constant, right? The second portion here is a function of whatever that argument is here. Our argument is omega t plus theta, right? Agree? You know one thing, when I do this, I'm going to go ahead and do it one time. That's going to be equal to the square root of 1 over t. And then I'm going to have the integral from 0 to t of Vm squared times that. I'm going to break this cosine squared of omega t plus theta up according to that. So I have to take the 2 out in front, and then I have 1 plus cosine of 2 omega t plus theta. And it really doesn't matter, 2 theta. It won't matter there, it's 2 theta, actually, dt. And when I do this part, this is a constant, it survives. When I go from 0 to t, this integrates to 0, so I'm left with this. I have, the t comes out, and I'm going to be equal to 1 over the square root of 2 times simply Vm. Because if I take a square root of Vm squared, I get Vm. Follow me on this class? Now here's the bottom line of this. You can play with this later. When you look at this, this is the RMS value. You'll notice the relationship between RMS and peak value is 1 over the square root of 2. So if my Vm was equal to 100 volts, just listen to me. If that's the magnitude, the RMS value would be 70.7 volts, or 1 over the square root of 2, which is 0.707 times that. 70 volts. It's about 70% the peak value. Everybody follow me on this? For a standard sinusoidal or cosinusoidal variation. That's real important. And here's why it's important. When you think about power, now I didn't spend much time on power yet, but now I'm about to. When you think about power and average power, P-av, right? Average power was equal to 1/2, right? Times Im squared Actually, let me just put this down. When I look at this, if I have a resistor, and I want to do it this way, if I have a resistor here, R, and I have a current I of t through it, right? I know that the instantaneous power, P of t, through there, would be equal to V times I of t, V of t times I of t. Well, V of t is just I of t times R, or it would be equal to R times I of t squared. Do y'all agree with that? The voltage here is just going to be I of t times R, isn't it? So V of t times I of t would really be R times I of t squared. Do y'all agree with this, class? All right? Now, if that's the case, what's the average value of power? Well, P_av, right, would be equal to 1 over t, the integral from 0 to t, of P of t, which is R, times I of t squared dt. Do you agree with that? Agreed? How many see this, right? I'm not trying to do something here that's hard to understand. I'm trying to just show you. If this is power, it's voltage times current, right? Voltage would be R times I of t, or really we get R times I of t squared, right? We come down here, what's the average value of power? Well, it would be 1 over t, the integral from 0 to t of R times magnitude times I of t squared, right? Now look, what is this? Well, if I take the R out in front, isn't P_av right here equal to R times the quantity, 1 over t, the integral of I of t squared dt from 0 to t. Follow me? I just took R in front there, right? What do you notice that is? Anybody? What's IRMS? Isn't that equal to the square root of 1 over t, the integral from 0 to t of I of t squared dt? Right? Following on this? Now, how many see this part at least, right? The definition. Square this. What do you get? Square both sides. Agreed? Why did I do that? Because that's what that is. And the power in a resistor can be given, the average power, you can say P_av in a resistor is equal to either, and then it would be R times I RMS squared, or it can be given as 1/2 R times I peak squared. The RMS value and the peak value are related by 1 over the square root of 2. Got it, everyone? And that's the thing you take from this. We'll be using this a lot. We always, by the way, almost all the standard power problems that we're going to be dealing with use the value of RMS power. And the reason that is because if you think about a DC value of power, and this you had back in the day when you had physics, if you just had a battery, something that's not time variant, with a voltage V, and you had a resistance R here, the actual power that would actually be dissipated, P of t here, would be equal to I of t times R of, or times V of t. Since there's no time variation, it's just going to be equal to V squared divided by R. And here's the way you think of RMS value. It's like the DC value of voltage. All right, it's equivalent to the DC value of voltage that would dissipate power. Does that make sense to people? So when you think about RMS, it's like the equivalent DC value of voltage, even though it's not DC, okay? Next thing, and I'm about out of time, I've got 150 on mine. Next thing we're gonna do, I didn't get to it yet, but we're gonna be talking about power factor, and I'm gonna give you some problems, basic problems on this, all right? Now, please show up Friday. I know, I'm gonna get a question. What's on the quiz Friday? It happens all the time. I'll do this. I won't give you a quiz if I see more than 2/3 of the class here. Otherwise, I'm going to give you a quiz on power. So it's up to you. And the 2/3 is my judgment call. One thing I'm going to do is I want you to come and do the homework because the next place that we're going is a little complicated. And if you're not here for that lecture, you're going to get in trouble.